This is EE300 Linear Circuit Analysis 2, Module 3, Video 2a, Bode Plots. In this video, we'll review previous work. We'll explore the idea of decibels. We'll look at Bode plots, and then we'll have a summary and previews of what's coming. So to review, previously we've done the sinusoidal steady state, and we had this big conclusion that if you put a sinusoid of a particular frequency into a linear circuit, what comes out is a sinusoid of the same frequency, but it's been scaled by the circuit gain at that frequency, and the angle has been changed by having the circuit phase angle added to the original phase. So if you put in a cosine of frequency omega A, amplitude V sub A, and phase phi sub A, out pops a cosine of frequency omega A, but the amplitude is now magnitude h of j omega A times V sub A, and the phase is now phi sub A plus the angle of j omega A. The magnitude of h of j omega A we call the gain at omega A, and the angle of h of j omega A we call the phase at omega A, and now we see the new amplitude is the original amplitude scaled by, multiplicatively, magnitude h of j omega A, and the new phase is additively added to the original phase phi sub A. It's the angle h of j omega added to phi sub A. So this captures h of j omega for all omega, if you plot it over a large enough range of omega, and the gain is the magnitude of h of j omega, and the phase is the angle of h of j omega. So we don't have to limit this to a particular frequency omega A. We can do this for a large range of frequencies. And then you can pick out the sinusoidal steady state gain and angle from the frequency response plots. So let's work an example. This is our standard RC circuit. We're looking at the gain across the output voltage across the capacitor. This time we've got a resistor of 10 k ohms and a capacitance of 1 microfarad. So when we do the network function, the transfer function, we get 1 over RC over S plus 1 over RC, and plug in these parameters. Since we've usually been using R of 1 k ohm and C of 1 microfarad, but now this is 10 k bigger, or the 10 ohms 10 times as big, and that makes 1 over RC 10 times as small. So we get 100 over S plus 100. So we can look at the magnitude, the frequency response here by plugging in j omega. And the magnitude then would be the magnitude of the numerator divided by the magnitude of the denominator. And the magnitude of the denominator is the square root of 100 squared plus omega squared. And we can factor out the 100 out of both numerator and denominator to get 1 over the square root of 1 plus omega over 100 squared. The angle of this, the angle of the numerator minus the angle of the denominator, the angle of a real number is 0, and the angle of 100 plus j omega is the inverse tangent of omega over 100. So now we can plot these, and here's our traditional first order output across the capacitor plot. The amplitude at low frequency is 1. You put it, the DC gain of the RC circuit there is going to be 1. When we go through the frequency 100, omega equals 100 radians per second, we get a gain of 1 over the square root of 2, and that's 0.707. And then you can see as you go to higher frequencies, you can if we look in this expression here where I'm highlighting the omega over 100, when omega is bigger than 100, that's all going to be bigger than 1. And so the whole thing is going to end up acting like 100 over omega. And you can see that behavior here at 1,000. Omega is 1,000, and 100 over 1,000 is 0.1. 2,000 is going to be 0.05 there. And you can see that behavior. The angle curve here, again, when the angle is low frequencies, you see just the angle, just a linear near 0 there. We'll talk more about that in the next video about the behavior of first order circuits. When we get to omega equals 100, then we have the inverse tangent of 1, which is 45 degrees, and it's a negative 45 degrees because that was in the denominator. And then let's see, it approaches asymptotically to 90 degrees. Okay, that's very nice. What about a different circuit? Here's a similar circuit, except now there's a resistor in the output branch also. So when we do the transfer function, we have R2 plus 1 over SC all over R1 plus R2 plus 1 over SC. We work through the math here. You clear this out, and you end up with R2 over R1 plus R2 times S plus 1 over R1 plus R2C all over S plus 1 over R2C. And when you plug in the numbers here, the term out front is 0.1. There's a 0 at 1,000, and there's a pole at 100. So same pole as the circuit before, but now there's a 0 at 1,000. the DC gain, if you plug in 0 here for S or J omega, those cancel out, and you're going to get a DC gain of 1 because you're going to have 10 from the fraction times 0.1. The high frequency gain here should be 0.1 because as omega gets big, J omega over J omega will dominate, and we'll just have 0.1. So let's see what that looks like. First, let's figure out what the magnitude of the frequency response is. So we do the same as before, except now it's the magnitude of the numerator. There's actually an omega in the numerator, so we get the square root of 1,000 squared plus omega squared, and then over the magnitude of the denominator, which is the square root of 100 squared plus omega squared. We can do the same factoring out, and so there's that one term we had earlier, and we have the square root of 1 plus omega over 1,000 squared over the square root of 1 plus omega over 100. The angle curve, well, it's going to be the angle of 0.1 plus the angle of j omega plus 100 minus the angle of j omega plus 100. And so the angle of 0.1 is 0, and the angle of j omega plus 100 is the inverse tangent of omega over 1,000. Excuse me, the angle of j omega plus 1,000 is the inverse tangent of omega over 1,000, and the angle of j omega plus 100 is again the inverse tangent of omega over 100. So we get arctan of omega over 1,000 minus the arctan of omega over 100. And now let's see what these look like. Well, it looks a lot like the first curve for very low frequencies. It's hard to tell them apart. I mean, you don't see in the magnitude curve, you don't see any difference between the two curves. It's only as you go to larger frequencies that you see the first filter with just the RC continue to roll off, whereas, as we said, the high frequency gain of the second circuit ought to be 0.1, and you can see it approaching 0.1 asymptotically there. The angle curve is a mess because of the second circuit, because it starts when omega is very much less than 1,000. This term is basically going to be 0, and it looks about like the original curve. But now you start to get the difference between the two arctangent curves, and you see that in the long run, as omega gets big in both these expressions, you're going to get 90 degrees minus 90 degrees. So it ought to go back to 0, but it's doing it pretty slowly. I mean, here we are at 1,000, 2,000 radians a second, and it's, not quite, it looks like it's even slowing down as it gets there. So how can we explore this kind of behavior where the changes happen and we need bigger ranges of frequency, and yet, they've got a pole back here at 1,000, we got an angle, a 0 to 1,000, a pole at 100, an angle at 1,000, and then it's going to, what happens is we keep increasing frequencies. And how could we distinguish between behaviors at, very small frequencies also? So here's the situation. The poles and zeros could be orders of magnitude apart. In this case, they were an order of magnitude apart, and there could be more poles and more zeros. So how would we tell what their effect is on the frequency response of the circuit? There could be small differences, and those could be hard to see. So if we let frequency vary on a logarithmic scale, we can have a wider range of frequencies in the same size plot. And then if we compress the amplitude, or if we expand the amplitude in a certain sense by plotting the gain in decibels, which is going to be a logarithmic way of looking at the gain, then we're looking at the magnitude curves on a log-log basis. And that has some nice properties that we'll see here and also in future videos. So we have to figure out what these decibel things are. I mean, I gave you the definition there, but there's a background to it. So here's our linear circuit, and we'd like to talk about what the power gain of the circuit is. We've got a signal coming in on this side, a sinusoidal signal, V cosine omega t. I dropped the A's because we know they're all going to change. We're looking at this over a large range of frequencies. So if I put in a sinusoid of frequency omega and amplitude V, what's going to be the power gain of the circuit? So what's the input power? And then what's the output power going to be? And we know the output of the circuit is going to be magnitude h of j omega times V times cos omega t plus the angle of h of j omega. So what's the input power? Let's assume that when we look at this here, that the load that V1 sees, the internal resistance here, the source resistance, if you will, or the load resistance seen from the point of view of the source attached up on this side, on the left side. And then when we hook this thing up to something else, let's assume they see the same resistance. That was a fairly common practice in the day. You wanted to have a standard set of terminations on your circuits when you had things like repeating amplifiers for the telephone signals and the like. So you had these amplifiers on telephone lines. And digital has made that all obsolete. So the concept remains, though, that they're going to look at the same load. Let's just call it R. So now we need the average power in the input signal. We have the instantaneous power would be V cos omega t squared over R. That's the instantaneous power. We're going to average that over one period of the sinusoid. So we divide by the period. We integrate it over the period to take the average there. And V squared, cos squared is a half of 1 plus a cosine twice the frequency. So the cosine twice the frequency integrates out over an integral number of periods, and we're left with that half term there. So the average power in the input signal is V squared over 2R. And in the output signal, we do the same thing, except we have the magnitude h of j omega, and we have the angle h of j omega. That's just a shift. That doesn't change the fact. So the squaring of the cosine works the same way. We still get the half on the average value of the cosine. So we get mag h of j omega squared v squared over 2r. And when we take the ratio of the second term, the second power, the output power to the input power, we just get magnitude of h of j omega squared. So bells, after Alexander Graham Bell, the inventor of the telephone, is a measure of power, the ratio of a log base 10 ratio of one power relative to another. So our power ratio in bells would be the log base 10 of the average output power over the average input power. Well, a decibel is a tenth of a bell. So if we want our power ratio in decibels, that would be 10 times the log base 10 of mag h j omega squared, because the original power ratio P2 over P1 would be mag h j omega squared. So if we're in decibels, we're going to have 10 log base 10 magnitude h j omega. There's a missing 10 over here. I knew I couldn't get through this video without a bug, but here it is. Here's a 10 that ought to be there if we're talking about the power in decibels, because if this is the power ratio in bells, then there's going to be 10 times as many decibels. So there should be a factor of 10 here. So there's the factor of 10. It's times log base 10 magnitude h of j omega squared. And by the properties of logarithms, that comes down to this 20 times the log base 10 magnitude of h of j omega. So the circuit gain in decibels is 20 times the log base 10, the magnitude of h of j omega, because the circuit gain in bells would be the log base 10 of this power ratio. And the power ratio is the magnitude squared of the frequency response. We're stuck with these historical terms. So here's a set of gains and their corresponding power gains. So if h of j omega is the circuit gain, then h of j omega squared would be the circuit power gain. So then here's the circuit gain in decibels, 20 log base 10 magnitude. No gain, 0 dB. Gain of root 2, which is a power gain of 2, is 3 dB. Circuit gain, an amplitude gain of 2 is a power gain of 4, and that's a 6 dB change in decibels. Somewhere in the middle between on a logarithmic scale between a gain of 1 and a gain of 10 is the square root of 10. And so that's a power gain of 10, and that has a gain in dB of 10. An amplitude gain of 5 is a power gain of 25. That's 14 dB gain in decibels. And then a gain of 7.07, or 10 over the square root of 2, is a power gain of 50, and that's a 17 dB gain. And then a gain of factor of 10 is a power of 100, and that's 20 dB. So every 20 dB factor is a multiplicative factor. Every increment of 20 dBs is a multiplicative factor of 10. And then the attenuation would work the same way. So if you've got an attenuation of 1 over root 2, then you have a power, it has half as much power coming out as went in. That's a 3 dB attenuation. If it's attenuation 0.5, the power gain is 1/4. That's a 6 dB attenuation, and we call it, so it's minus 6 dB, etc. So you can read the rest of these off here. Again, 1 over root 10 is 1/10 of root 10, and so that's got a minus 10 dB. Scale gain of 0.2, where 1/5 the amplitude is 1/25 the power. It's minus 14 dB. Root 2 over 10 is 0.02 of the power coming out, just 1/50th of the power. and that's 17 dB attenuation. And then if the gain is 0.1, so a tenth, the amplitude on the outside is output is a tenth is what it was on the input, is a hundredth as much power, and that's a 20 dB attenuation. So when we put this into, here's our two transfer functions again. We put this frequency axis is logarithmic. We put the gain in decibels and the angle in degrees. And so here's what these plots look like when they're done as Bode plots. The magnitude now is 20 log base 10 of the magnitude, the gain of the frequency response. And now you see there's that 1 over root 2 showing up as minus 3 dB. And we see the 1 over omega behavior show up as a straight line with a slope of minus 20 dB. And we call this multiplicative factor of 10 in the frequency a decade. So this thing attenuates by 20 dB per decade. In the second curve, we see the high frequency gain of 0.1 showing up as a high frequency gain in dB of minus 20 dB, an attenuation of 20 dB. And we see that at the zero frequency, where the frequency was 1,000, now we see that it's 3 dB higher than the high frequency asymptote there. We also see in the original circuit, the angle curve goes to minus 40 degrees at the pole value of 100, and then it attenuates, then it approximates, goes to asymptotically to minus 90 degrees, and you start to see that because we're up to a frequency of 10,000 radians a second now, and we can see the minus 90 showing up. And we can also see that the second transfer function, we can see how the angle starts to go in trying to get back to 0 degrees as it ought to for high frequencies. We'll talk more about this for the first order circuits in the next video. So to summarize, decibels is the decibels is 10 times the log base 10, the ratio of one power to another. And when you talk about the filter gain, then that makes that 20 times the log base 10 the magnitude, since the power ratio would be the magnitude squared. The Bode plot is the gain in decibels versus frequency on a log scale, and the angle in degrees versus frequency on a log scale. And it lets us look at the circuit behavior over many orders of magnitude of frequency, and we can tell the difference between small differences because of the logarithmic effect. And we can also see how the high frequency behavior, which is like 1 over omega, shows up as a straight line behavior on the log-log plot. So next we'll look at first order circuits and in terms of circuit behavior. I mean, what's happening with the resistance and capacitance and the currents and the voltages. And the next video after that, we'll look at second order circuits, both wideband and narrowband. So this has been Module 3, Video 2a, Bode Plots. This is EE300 Linear Circuit Analysis 2.